Welcome to qnawire.
In this question, we have this setup. So inside there's a line charge plus lambda, and then it's also surrounded by a cylindrical coaxial shell with a charge density negative lambda. And so in this capacitor arrangement, we want to find out the energy density, the energy per unit length, and using different methods to calculate the energy per unit length and to show that they are consistent. Okay, so in part A, we want to find the energy density. Okay, so the energy density formula is half epsilon naught E square. Okay, the E here is electric field. Okay, the electric field due to line charge, we are referring to the region inside here. Okay, so between RA to RB. Okay, because that's the space that the electric field is non-zero. Okay, because the rest are all conductors, so the electric field inside they are zero. Okay, so the electric field in due to line charge. Okay, in the region from RA to RB, okay, the only charge distribution that matters is the one that is in the middle. Okay, the inner cylindrical wire. Okay, the one at the cylindrical shell doesn't contribute. Okay, because of Gauss's law. Okay, so the electric field due to line charge. Okay, okay, so this one referring to the chapter in Gauss's law, we have lambda over 2 pi epsilon naught r. Okay, so then you can just substitute. Okay, energy density A equals to half epsilon naught E square, then this is equal to half epsilon naught lambda divided by 2 pi epsilon naught r, and then the whole thing square. So if you simplify, you get lambda square over 8 pi square epsilon naught r square. Okay, so this is the expression for energy density. Okay, then in part B, we want to find the energy per unit length. Okay, so energy, okay, given the energy density, it will just be integral of u sub e dv. Okay, and in this case, our dv is a cylinder, is a volume of a cylindrical shell, so it will be 2 pi r dr times l. Okay, and ue is the expression in part A. Right, so we have plenty of constants. For example, we also cancel out some things. Okay, so we have lambda square over lambda square L over 4 epsilon naught. Okay, one of the R cancels. Okay, so you have integrate from RA to RB, 1 over R dr. Okay, then there's a square. So okay, so the cancellation actually gives us 4 pi. Okay, so you cancel one of the pi, cancel the 8, you get 4. And then you get lambda square L over 4 pi epsilon naught. Okay, and then you do the integration. Okay, you can natural log RB divided by RA. Okay. Okay, then energy per unit length. Okay, energy per unit length. Okay, this is U over L. So this expression is U. Okay, U divided by L will be lambda square divided by 4 pi epsilon naught. natural log, okay, RB divided by RA. Okay, so this is the answer for part B. Okay, next in part C, we are going to use another method to obtain try to obtain energy per unit length. Okay, so first we note that the potential difference. Okay, so this is equal to potential difference due to or in this configuration, potential difference between the center line charge and the shell and the cylindrical shell. Okay, so this is equal to lambda over 2 pi epsilon naught natural log RB divided by RA. Okay, so this can be obtained using delta V equals to negative E dot EL. Okay, and then the E is lambda over 2 pi epsilon naught. Okay, R. Okay, and you integrate from RA to RB. Okay, and you get the delta V to be to have this magnitude. Okay, we are interested in the magnitude in this case. Okay, and then we also have the capacitance per unit length. Okay, so this is C over L, and this is 2 pi epsilon naught divided by natural log RB divided by RA. Okay, and then our U over L is half CV square times 1 over L. Okay, so this part is actually our U. Okay, and then you multiply by 1 over L. So you have half C over L times V square. So you can actually put in all the expressions. Okay, the V is lambda over 2 pi epsilon naught natural log RB divided by RA, and then this thing square. Okay, okay, so if you simplify the term, okay, you have half. Okay, so the so so you can actually to simplify this algebra, okay, you can see that the 2 pi epsilon naught here will get cancelled out. This will also get cancelled out by these two terms, right? But the square, you can cancel the square and then just attach the square to the lambda square, and then you are good. Okay, so lambda square over 2 pi epsilon naught natural log RB divided by RA. Okay, and then you have lambda square over 4 pi epsilon naught natural log RB divided by RA. Okay, so if you compare this expression with the expression in part B, you see that they are the same. Okay, so agree with part B. Okay, and that's all for this question.